40 kilograms of water every second. This was discovered by NASA's Swift Observatory while observing the comet Atlas, not at perihelion. Not when the comet approached the Sun, maximizing solar radiation at a distance of 2.9 astronomical units, where water barely sublimates, disappearing behind our star, hidden from all telescopes on Earth, precisely when everything becomes most intense. If you want to stay updated, like and comment where you're listening from, what time it is, and whether you think this is just extreme comet activity or something entirely different. Chapter 1. The Mystery of the Water Hose. Swift's observations, published on September 30th in the journal Astrophysical Letters, are not just unusual, they break all the rules. Dennis Bodovitz and his team from Auburn University spent over 2 hours capturing ultraviolet images to catch the hydroxyl trail, a characteristic glow that occurs when sunlight breaks apart water molecules. What they discovered became a true challenge for predictions based on distance. At such a distance from the Sun, comets usually show activity at 3 to 5%, but Atlas's 3 eyes show at least 8%, almost double. But then the strangest thing begins. The math doesn't add up with the pure sublimation of the surface. Even considering the solar heating at a distance of 2.9 astronomical units, the energy contribution is insufficient to explain the output of 40 kilograms of water per second from a core estimated to be 5 to 6 kilometers in diameter, unless something else is happening. Observations in the near-infrared range from the Gemini South telescopes and NASA's infrared telescope provided clues to the puzzle. In the coma were icy fragments, not just steam, real chunks of ice hanging in the clouds around the core. When exposed to even weak sunlight, these fragments heat up faster than the surface of the ice due to their greater surface area to volume ratio. Each of them becomes a miniature steam vent, hundreds or thousands of such fragments scattered across the region, all contributing to the overall release of water. As a result, it seems that the core is much more active than it actually is. As noted by Zexi Xing, the lead author of the study, every interstellar comet has been a surprise. Oumuamua was dry, Borisov rich in carbon monoxide, and now Atlas is ejecting water at distances we did not expect. Each of them rewrites our understanding of comets. But why are these icy fragments even there? Did an event of fragmentation occur at Atlas's 3 eyes before the comet could be detected? Are these remnants of millions of years of micrometeorite impacts during its interstellar journey? Or do comets from a dense disk of the galaxy behave this way, having a completely different structure, as they formed under conditions that our solar system has never experienced? The time frames add another layer of mystery. The comet 3-eyed Atlas disappeared from the view of the Swift telescope in August, getting too close to the Sun for safe observation. However, in early October, when the Martian orbiters caught it while passing at a distance of 30 million kilometers, the coma was clearly visible for several thousand kilometers, confirming its activity. The comet continues to lose water as it approaches perihelion, and this key word is approaching. At this moment, the 3-eyed Atlas enters into a solar conjunction, and the Earth and the comet are on opposite sides of the Sun. No ground-based telescope can track it through the bright sunlight. The comet's perihelion will reach on October 29th at a distance of 1.36 astronomical units, completely hidden from our view. Solar radiation in this area will be several times stronger than what Swift recorded. If the baseline water emission was 40 kilograms per second at a distance of 3 astronomical units, what will happen at a distance of 1.14? The educational answer is obvious. The comet must shine significantly brighter, and the coma should expand. Supervolatile substances such as carbon dioxide and carbon monoxide, which sublimate at lower temperatures, must be rapidly ejected into space. The tails should grow into spectacular streams millions of kilometers long. We have observed this pattern hundreds of times with the comets of the solar system. But the 3-eyed Atlas has already shown that one should not rely on academic predictions. Water activity at a distance of 2.9 hundredths of an astronomical unit should not have manifested. 8% of the active surface was also not in the forecasts. The icy field of debris in the coma was a surprise for us. Thus, what will happen during the hidden passage of perihelion remains a true mystery. The spacecraft JWST will certainly get the best view. From November 2nd to 25th, after the 3-eyed Atlas appears from behind the Sun, JWST will observe using cameras, spectrometers, and particle sensors. A unique position will allow observing the comet from a distance far enough from the Sun for visibility, yet close enough to capture details of its activity after perihelion. The problem? Data transmission. At the moment, JWST is using its high-gain antenna as a thermal shield, relying on a slower backup antenna to transmit data to Earth. We won't see data from November until February 26th. 3 months of waiting. 3 months of uncertainty about whether the comet survived perihelion. Did it split like Shoemaker Levy 9 under Jupiter's tidal forces, or did some completely unexpected events occur in those hidden days behind the sun? There is one more consideration, what Denis Bodovich mentioned in passing but did not emphasize. Walter is the universal standard in comet science, a basic model for measuring activity and determining composition. But the three-eyed Atlas is not a comet of the solar system. It is a messenger from a planetary system of another star, a system that possibly formed 10 billion years ago in the dense disk of our galaxy. The protoplanetary disk in which this object formed had different temperatures, compositions, and chemical gradients compared to those that formed Earth and Jupiter. The water we discovered may be chemically identical to ours, with hydrogen and oxygen in the familiar configuration, but the context remains alien. The ratios of isotopes, trace elements mixed with main components, the structure of ice crystals, all carry information about a star system we will never visit. We have recorded hydroxyl, the broken remnants of water molecules. However, hydroxyl can also arise from other molecules. Organic compounds, alcohols, complex chemistry occurs in a coma when sunlight and cosmic rays break down larger molecules into fragments. 40 kilograms per second can represent pure water, or a mixture of water and other volatile substances that create similar spectral signatures. We need higher resolution spectroscopy to know for sure. We need longer observation windows. We need the comet to survive perihelion and remain active as it heads back into interstellar space. Because there is another reality. 3 Atlas will not return. After passing Jupiter in March 2026, it will leave us forever. This is our only chance to study the comet from the galactic thick disk. Populations of ancient star systems that we have never explored before. Every observation matters. Each data point is irreplaceable. The flow of water is just a prelude. It indicates that 3 Atlas moons are rich in volatile substances, structurally unusual, actively emitting gases at distances where comets of the solar system remain dormant. But the main event will take place next month, behind the sun, hidden from sight, where the rules of comet behavior will either be confirmed or completely shattered. And when JWST finally receives its observations in November, when the comet becomes visible with what happened to it during perihelion, we will know whether the loss of water was a harbinger or a warning. We will see whether the 3 Atlas are simply an exceptionally active comet or something that requires a complete rewrite of textbooks. The answer awaits us, hidden. 50 days from revelation. Chapter 2. The hypothesis of the mothership Leob. Changing the rating on the Leob scale from 4 to 6 in 2 weeks is no small leap. In a system where 0 means definitely natural and 10 means definitely technological, the shift from 4 to 6 represents a fundamental change in the assessment of probability, and Leob does not make such changes lightly. Each unit on its scale requires quantitative anomalies, statistical outliers that resist traditional explanation. By mid-August, 3 Atlas AIs had accumulated enough such anomalies to shift the needle into a zone that makes most astronomers extremely uneasy. Let me start with the probability of a trajectory that continues to be fixed and rejected, 0.500%. The probability that an interstellar object accidentally entering our solar system will pass as close to Venus, Mars, and Jupiter as the triple object Tri-I Atlas does is 5 out of 100,000. Loeb and his team calculated this probability using orbital mechanics and time windows, considering the movement of planets and narrow approaches. The mathematics here is simple. An object on a retrograde hyperbolic orbit entering from the direction of the Sagittarius constellation has a tiny probability cone for each interaction with planets. The cumulative probability of colliding with 3 such cones approaches 0. Critics argue that we select facts based on existing data, and if we consider enough interstellar objects, eventually one of them will have an unlikely trajectory simply by chance. It's true, but we discovered only 3 interstellar visitors, and one of them just passed through the eye of the needle, granting access to the 3 most interesting rocky bodies in the inner part of the solar system. The Bayesian prior in this case, that is, the probability we would assign without considering other evidence, causes discomfort. At the time of perihelion, on October 29th, during the solar conjunction, Earth and the three moons of Atlas are on opposite sides of the Sun, making observations from Earth impossible at the most critical moment. If you wanted to perform a maneuver to change momentum, perihelion is the optimal point. You move faster relative to the Sun, and each kilogram of fuel provides the maximum speed increase. This is called the Oberth effect. Spacecraft constantly utilize this principle, and the three Atlas probes reach perihelion precisely when we cannot see them. Loeb calculated the required speed increase for mini-probes released at perihelion to achieve Earth's orbit. Calculations show that this is possible. A small probe can weigh 10 kilograms and use a propulsion system with a specific impulse of about 300 seconds. It can perform a reverse Oberth maneuver and insert itself into a stable orbit around the Earth. The arrival window is from late November to early December, just when the three Atlas moons emerge from behind the Sun, and we begin to look for changes after perihelion. Is this the plan? Or do we see patterns in randomness because people tend to seek patterns, and Loeb prepared us to look for such patterns? The discrepancy in the object's size remains unresolved. The first brightness measurements indicated a 20-kilometer core, which was absurdly large for an interstellar object if the albedo was typical for asteroids. Oumuamua was only a few hundred meters in size, and Borisov was less than a kilometer. The appearance of a 20-kilometer comet in our solar system would be a statistical nightmare, an event that should not occur within a human lifetime. But then Hubble allowed the comet, and the estimates dropped to 5 or 6 kilometers, based on the actual brightness of the core compared to the overall brightness of the system, including dust. It's still a lot, still unusual, but within the acceptable limits for a natural object. Early brightness measurements were not mistaken. They were real. The three-eyed Atlas indeed appeared brighter than it should for a comet 5 kilometers away. Loeb suggests this may be related to reflective properties. If there are metallic components on the surface, if the shape focuses the reflected light, if the material properties are radically different from porous ice and dust, then we obtain anomalous brightness. The object may appear larger than it actually is, and this could very well be a natural phenomenon. Gastroids exist, but combined with all other factors, it increases the likelihood of unusual origins. Then there is the configuration of dust. Hubble images show the maximum density of dust on the sunlit side. Heavy particles, too massive to be moved by radiation pressure, are concentrated ahead of the core in the direction of its movement. The standard gas emission of a comet should create jets perpendicular to the surface based on local heating patterns. These jets can be directed in any direction depending on the axis of rotation and the distribution of volatile substances. But a stable ejection of dust towards the sun requires either a very specific axis of rotation or orientation, or something else that constantly ejects material in the direction of motion, regardless of which hemisphere faces the sun. Loeb notes that this corresponds to debris ejection during high-speed transit through the interstellar medium. If a three-eyed Atlas travels at a speed of 60 to 70 kilometers per second for millions of years, collisions with interstellar hydrogen atoms are not trivial. Each collision releases energy, and with enough impacts, erosion of the front surface begins. The dust we observe may be ejected as a result of impacts, material constantly stripped away by pressure, as the object moves through space. This is a natural explanation, but it also aligns with emissions from internal systems, with orientation control engines that maintain position, with many technological processes that can cause similar observations. The rotation period of 16 and a fraction hours lies in the middle of the uncertainty range. It is too slow to be a result of gas release and too fast to be tidally captured by anything. For a comet made of loose debris held by weak gravity, the rotation is stable and unremarkable. For solid objects, whether natural or artificial, the rotation will be equally stable and unexpressive. This does not lead us to any definite conclusions. However, the angle of approach is harder to ignore. The direction from Sagittarius means that the object is moving towards the galactic center, the most densely populated and brightest area of the sky. Detecting it against this backdrop is extremely difficult. We notice the three-eyed Atlas only because the Atlas survey telescopes are specifically designed to detect fast-moving objects, and even then, we nearly missed it. The first detection images date back to mid-June, but the object was barely visible at the 20th stellar magnitude. If we had paid attention to it a few weeks ago, we would have had no observations. It would have passed through the inner solar system completely unnoticed. If you plan a reconnaissance mission to an alien solar system, approaching from the direction of the galactic center is tactically wise. You arrive, shrouded in background light, giving the inhabitants minimal warning. By the time the discovery occurs, you are already deep in the system, and it is too late for any significant response. Is it so? Or is this yet another case of trying to assign intention to randomness? Early spectroscopic confusions add another data point. Several teams reported that in the first weeks they found no carbon-containing molecules. There was no clear signal of water, only reddish dust and uncertain absorption features. It looked active, but not like a comet. Low-Barged claimed it was a compromising signal, proof that Tri-Eye Atlas was not behaving like a natural comet. When new observations arrived, water was detected. Carbon dioxide dominated the coma. Spectral signatures began to match cometary expectations. The Low-Barged takes its position but notes that the initial uncertainty remains unexplained. Why did the comet take so long to show standard flying signatures? Why was there early confusion? One possibility is observational bias. Early spectra had low resolution, short exposure times, and were captured when the comet was still faint. As it brightened and more advanced instruments began to record it, the data improved. What appeared to be the absence of volatile substances was actually just a lack of sufficient signal-to-noise ratio. This is a dull answer. Probably, it is the correct answer. But the word probably plays a significant role here. Low B does not claim complete certainty. He claims that we must explore, that the probability is not zero, that the consequences of error when we dismiss a technological artifact as a comet, because comets are common and artifacts are not, will be catastrophic for our understanding of intelligence in the universe. He wants the Galileo Project Observatory to monitor secondary evidence in November and December. If the Three-Eye Atlas releases probes, and if these probes enter Earth's atmosphere to study our planet up close, it may lead to an increase in identified aerial phenomena, objects moving in ways that contradict traditional aerodynamics, objects that do not conform to natural or human technologies. How likely is that? No. Lubodmitz believes that the chances are more for a natural comet, but they are not 100%, and it is in this gap between high probability and absolute certainty that the entire field of technosignature research exists. We have spent 60 years listening to radio signals from extraterrestrial civilizations. We built huge telescopes to catch laser flashes from distant stars. We analyzed millions of stellar spectra in search of atmospheric biosignatures on exoplanets, but we never seriously considered the possibility that artifacts could come to us. Interstellar objects, the very things we began to discover over the last 8 years, may include probes along with rocks. 3A Atlas is a test case, an object that compels us to develop methods for distinguishing between natural and artificial at interstellar distances. Such methods do not exist yet. We have brightness curves, spectra, and trajectory analysis, but we lack a reliable basis to assert that this is definitely a natural phenomenon, or that it requires further study. Loeb attempts to create such a foundation in real time, using a triple atlas as a calibration object. The hypothesis of the mothership is elegant in its terrifying context. It is inefficient to send one probe to one star. Instead, they send motherships on long, slow trajectories between interesting star systems. Each mothership carries dozens or hundreds of smaller probes. As it passes through a system, it releases probes specifically designed to study individual planets. These probes are disposable, small, and easy to produce. The mothership continues its journey to the next star and beyond, mapping the galaxy for millions of years. From the perspective of the civilization that launched it, the return on investment is colossal. One mothership can service thousands of systems, and we will never notice its approach. The mothership will be dark, cold, indistinguishable from a comet or asteroid until it starts releasing probes. By then, it will be too late. The drones are already in flight, approaching their targets, and even if we detect them, we won't be able to intercept them. Not with current technologies, not without decades of warning. Loeb suggested a time frame. If the probes are launched on October 29th during the hidden perihelion passage, using Oberth maneuvers to slow down and capture into Earth's orbit, they will arrive between November 21st and December 5th. We are talking about objects potentially the size of a shoebox, Or perhaps even smaller. The Earth Space Observation Network tracks objects as small as 10 centimeters in low orbit, but this concerns objects we expect to see. Objects with predictable orbits, something entering from interstellar space, something with an active propulsion system and maneuverability, can easily avoid detection. Will they contact us? Will they remain hidden? Will they study us from orbit, land on the surface, or just observe and report back? These are the questions that keep Loeb awake at night, because the answer determines everything. If they are peaceful explorers, xenoarchaeologists of some ancient galactic civilization, then the first contact could become the most important moment in human history. If, however, it is something else. If the dark forest hypothesis is true, revealing one's location in the galaxy means a death sentence. Perhaps we have already realized the danger too late. The Galileo Project's observatories will monitor the situation. 3 sites, continuous monitoring, complete sky coverage. Any anomalies from November to December will be documented, analyzed, and published. If nothing happens, if the Triple Atlas behaves like a comet and the probes do not arrive, the hypothesis will lose its validity. The rating on the Loeb scale will drop back down. We will classify the Triple Atlas as interesting but natural and move on. But if something happens, if we discover objects that shouldn't be in their place, moving in an unusual way and appearing exactly when Loeb predicted their appearance, then we will face a problem or an opportunity, depending on what happens next. Chapter 3. October 29th. Behind the Sun. A solar conjunction shouldn't be this dramatic. Most comets pass behind the Sun, disappearing from sight for days or weeks, and then reappear on the other side, usually looking predictable. They become brighter if they survived, or fragment if they did not. Astronomers have observed this pattern for centuries, and we know what to expect. However, the comet Tri-I Atlas reaches perihelion at a distance of 1/3600th of an astronomical unit on October 29th, completely hidden by sunlight, and the uncertainty of what will happen next plunges the community into uncharted waters. Geometry is cruel. The Earth and the comet are on opposite sides of the Sun at an angular distance that makes ground observations impossible. It's impossible to point a telescope at an object 12 degrees from the Sun without damaging the instrument and blinding the detectors. Sunlight suppresses everything. Even telescopes in space, like Hubble, have strict exclusion zones for sunlight. Coronagraphs like SOHO can catch a glimmer, but Tri-I Atlas will likely be too dim and too far from the solar limit to register against the scattered light. For about 6 weeks, from early October to mid-November, we remain blind. But the perihelion is not only about visibility. It's a question of physics. At a distance of 1/3600th of an astronomical unit, the solar flux is strong enough to vaporize all volatile compounds on the surface of the comet. Solar radiation actively sublimates. Carbon dioxide, which was the dominant gas in the coma based on observations from JWST, transitions from solid to vapor almost instantly. Carbon monoxide, ammonia, methane, and any supervolatile substances trapped in an icy matrix are all released simultaneously. The core must become a press, gas escaping through cracks and vents, dust lifted by expanding steam, a mass swelling to millions of kilometers, a tail stretching behind like a banner. This is the model. This is what all textbooks predict. But the model assumes that we understand the composition and structure of the Tri-I Atlas, while in reality, we do not. The JWST data from August 6th showed something unexpected. The ratio of carbon dioxide to water is 8:1. This is one of the highest values ever recorded for a comet. Comets of the solar system show ratios closer to 1:1 or even hydrogen-dominated chemistry. Carbon dioxide is common but rarely a primary volatile. The Tri-I Atlas changes this ratio. This is a comet made of dry ice, where water is a secondary component. This changes everything about how perihelion should behave. Carbon dioxide sublimates at significantly lower temperatures than water ice. At a distance of 1/3600th of an astronomical unit, the surface temperature on the sunlit side can reach 200 kelvins or higher, significantly above the sublimation point of carbon dioxide, which starts at around 150 kelvins. At the same time, water ice requires a temperature of about 270 Kelvin to sublimate effectively, which is why we observe a difference in processes. Carbon dioxide instantly explodes from the surface. Water trapped under ice or mixed with its matrix sublimates more slowly, resulting in a two-step gas release. First, a powerful burst of carbon dioxide occurs, creating a bright and rapidly expanding comet. Then follows a slower and more prolonged release of steam as the upper layers break apart, revealing deeper layers of ice. However, there are complications. If carbon dioxide dominates and is released sharply, it can sweep away layers of dust, isolating the water ice. As soon as this isolation disappears, sunlight penetrates deeper, and the sublimation of water accelerates. A comet can transition from a carbon dioxide-dominated system to a water-dominated system in just a few hours or days, and we will not see this process. We will only see its consequences when the JWST station conducts its observations in November. There is another scenario that no one wants to discuss in official documents, but which is talked about at conferences. What if the comet breaks apart? Perihelion stress is a reality. The combination of thermal shock, internal pressure from gas emissions, and tidal forces from the sun's gravity can tear apart loosely bound objects. We have already observed this. Comet Shoemaker Levy 9 broke into more than 20 pieces before colliding with Jupiter. The BLR comet broke apart in the 18th century and never recovered. Recently, the Atlas C2019Y4 comet disintegrated in 2020 as it approached the Sun, turning into a cloud of fragments. The comet REI Atlas has a rotation period of 16.16 hours. This is slow enough for centrifugal forces to be negligible. Gravity must hold it together, but the object has traveled through interstellar space for billions of years. Radiation from cosmic rays, temperature fluctuations between near absolute zero, and the heat received from passing close to other stars, impacts from micrometeoroids, internal cavities from the loss of volatile components over geological timescales. Structural integrity can be compromised in ways that we cannot determine through spectroscopy or photometry. If the comet breaks apart, it will reflect on the light curve. A sudden increase in brightness as a large surface opens up, followed by a quick dimming as fragments scatter, and the overall cross-sectional area decreases. By the time of JWST's observations in November, we will see several condensations, individual nuclei, each with its own coma, elongated along the orbital path. This will be scientifically exciting. Simple samples from the depths of an interstellar comet revealing compositional gradients. But this will also mean that we miss the very moment of fragmentation, the moment of rupture, the forces at play as the material split. All of this happened beyond the Sun, where we could not capture it. Then there is the load scenario, which views perihelion as an opportunity rather than a threat. If 3 Eagles are technological and have maneuvering or thrust capabilities, they should be used at perihelion. The Oberth effect enhances every kilogram of thrust. A small fuel burn at perihelion leads to speed changes that would require significantly more fuel at apogee. If the goal is to release probes that will enter planetary orbits, they should be released right here. The calculations are clear. October 29th is the optimal time for this. Load calculated the exact parameters. A 10-kilogram probe with a chemical rocket capable of changing speed by 500 meters per second could enter a highly elliptical orbit around Earth, with a periapsis at about 400 kilometers and an apoapsis beyond the Moon. From this orbit, the probe could study the Earth's atmosphere, oceans, electromagnetic emissions, everything visible from space. He could transmit data back to 3 satellites before the mothership left the solar system, or remain idle, observing and recording information for later retrieval. The arrival window occurs at the end of November, from the 21st to the 5th of December, depending on the exact moment of liberation and trajectory. This assumes that the probes use minimal correction maneuvers during flight. If they have more fuel and more complex guidance systems, the arrival window widens. We may see them earlier or later and also completely miss them if they change course to avoid detection. And so the awkward question arises: will we recognize them at all? Our space observation network tracks cataloged objects, satellites, debris, and spent rocket stages. We know where they are and where they should be, according to orbital mechanics. The appearance of something new on an unexpected orbit would cause alarm, but the reaction time is not instantaneous. By the time we identify the anomaly, investigate its origin, and rule out natural explanations, the probe could have completed its main mission and changed its orbit again. Loeb instructed the Galileo Project observatories to monitor this closely. 3 platforms conduct continuous surveys of the entire sky in optical, infrared, and radio wavelengths. Any transient event, any object moving along a trajectory that does not conform to standard ballistic paths, is marked for analysis. From November to December, the detection threshold will be lowered. The number of positive results will increase, but so will sensitivity. If something appears, they will see it. NASA and ESA have not officially commented on this aspect. Their focus is on the hypothesis of a natural comet. But behind closed doors, people pay attention to this. Space agencies have protocols for unidentified objects, not for UFO protocols or alien contact scenarios, but for unexpected debris, untracked satellites, and potential collisions. These protocols can be adapted if an object appears in Earth's orbit without a launch history, catalog entry, or plausible natural origin. The protocols activate, tracking intensifies, military forces are deployed, and the international community begins to ask questions. October 29th, just 6 days until this record becomes available. The three-eyed Atlas has already become invisible, absorbed by sunlight. The last ground observations were made at the end of September. Mars orbiters captured images of it during the flyby on October 3rd, showing a comet behaving normally with a noticeable coma. The production of dust corresponds to solar heating. Nothing abnormal, nothing that could indicate technology or fragmentation or a crisis. But the perihelion is a different matter. Perihelion is the point where thermal stress peaks, where internal pressures exceed structural limits, where decisions are made, if possible. In 6 days, the three-eyed Atlas will be closer to the Sun than ever in its multi-billion-year history. The surface temperature will rise sharply, the gas emission rate will increase, and we will not see it. The only real-time data will come from heliospheric observatories. The Parker space probe is far from the desired position, but Stereo and Dream can catch something by observing scattered light and brightness fluctuations if the three-eyed Atlas produces a powerful outburst. If the coma expands quickly enough, the solar monitoring satellites will be able to detect changes in scattered solar radiation. This will be indirect observation, with low resolution, but still something, a data point in the blind period. Then we wait for data from JWST. The spacecraft is perfectly positioned for observations after perihelion. From November 2nd to 25th, he will conduct observations using several instruments: a Janus camera for photography, a main spectrometer for composition analysis, a PET particle detector for studying the coma's environment, and a UV spectrograph for identifying volatile substances. All of this will be directed at the three-eyed Atlas as it emerges from behind the Sun, still bright from perihelion heating, potentially fragmented, perhaps with an impressive tail, possibly doing something that no one could predict. But the data will not arrive before the 20th or 26th of February. At the moment, JWST is using its high-gain antenna as a thermal shield, relying on a medium-gain antenna for communication. Data transfer speed is slow. Priority is given to observations, so images and spectra are stored on board, awaiting their turn to upload when bandwidth allows. By the time we see data from JWST in November, the three-eyed Atlas will have passed Venus, heading back to the asteroid belt, already cooling and dimming. 3 months of delay, speculation, discussions, and competing interpretations. Did the comet survive? Was it destroyed? Did anything unusual happen during the hidden perihelion passage? The answer already exists. It is in the photons traveling from JWST to Earth at the speed of light, but we cannot obtain it, cannot know it until the data arrives, is processed, and published for the scientific community. This is the cost of observations at interstellar distances using spacecraft from the solar system. We gain unprecedented views from unique perspectives, but we pay for it with time, waiting, and uncertainty that stretches over months instead of hours. October 29th is a turning point. Before this date, the Three Eyes Comet is an unusual but explainable object approaching the Sun, interesting but not revolutionary. After this date, it becomes what its perihelion defines it: a fragmented field of debris, a bright comet with a massive tail, a dormant object that remains intact but inactive, or something else that will require new categories, terminology, and new frameworks for interpretation. The Sun hides the answer, not forever, but just long enough for the waiting to become unbearable. Fourth point, carbon dioxide anomaly. The James Webb Space Telescope observed the Three Eyes Comet on August 6th at a distance of 3.32 astronomical units from the Sun. The NISPEC instrument, designed to capture infrared signatures invisible to optical telescopes, recorded spectral images in the range from 0.6 to 5.3 micrometers. What was obtained turned out to be not just unusual, but a chemical profile that is not found anywhere else in our catalog of observed comets. The ratio of carbon dioxide to water is 7.6 to 1. In comparison, the next largest recorded ratio, excluding the extreme outlier, C2016R2, is below 3 to 1. The Three Eyes comet is not only rich in carbon dioxide, but it also dominates this metric to such an extent that it calls into question our models of comet formation. Martin Cordner from NASA Goddard led the analytical group. An article uploaded in late August details the observations. The coma shows enhanced gas emissions on the sunlit side, fully aligning with expectations from solar heating. Water is present. Carbon disulfide is detected in preliminary detections. Ice water appears in spectral signatures. Dust scattering is noticeable in the near and far infrared ranges. All of this is normal and corresponds to comet behavior, except for this ratio. The ratio of 7.6 to 1 exceeds the trend for long-period comets and Jupiter family comets at similar heliocentric distances by 4.5 sigmas. In statistical terms, sigma measures standard deviation. 1 sigma is a normal fluctuation. 2 sigmas are noteworthy. 3 sigmas are rare. 4.5 sigmas indicate that something has gone very wrong or that something is fundamentally different. When the deviations are so great, you begin to doubt whether your sample is relevant for comparison. Perhaps the Three Eyes comet is not an anomaly. Perhaps it is an entirely different population, and we are comparing apples to something that isn't even a fruit. The ratios of carbon isotopes provide another clue. The Webb telescope recorded both carbon-12 and carbon-13 in the emissions of the coma. The ratio between them is within the ranges found on Earth and in the solar system. This indicates that carbon formed in a similar stellar environment, not in a population of triple stars from the early universe, where metallicity was close to zero, not in a carbon star enriched with unusual nucleosynthesis products, just ordinary carbon from an ordinary star. However, the high carbon dioxide content compared to water tells a different story about where and how ice formed. There are 2 main theories, each with its drawbacks. The first theory is related to radiation processes. If the comet Tri-Aya Atlas formed in a protoplanetary disk subjected to intense ultraviolet radiation from a hot young star, or spent billions of years in interstellar space under cosmic ray bombardment, then the water ice could have been partially destroyed. Water molecules break down more easily than carbon dioxide molecules. High-energy photons and particles act on ice, breaking the bonds between hydrogen and oxygen, and the released hydrogen escapes into space because it is very light. Oxygen can combine with carbon, forming more carbon dioxide. Over geological timescales, a comet initially rich in water could become rich in carbon dioxide through this process. The problem with this theory lies in the quantitative assessments. To change the ratio of a comet, initially composed of roughly equal parts water and carbon dioxide, to a ratio of 8 to 1 in favor of carbon dioxide, extreme radiation exposure is required over vast periods. It is about billions of years in the interstellar medium without any shielding. This is likely for Tri-Aya Atlas, considering its possible age, but also requires that water ice remains on the surface all this time. If a comet has a protective layer of dust or an internal structure that shields deeper ice from radiation, the processing efficiency sharply decreases. In this case, a gradient forms. The surface ice is heavily processed, while the inner ice remains untouched. When the comet becomes active and starts shedding layers, the ratio should change as deeper material is revealed. However, we do not yet observe such changes. The ratio remains unchanged between observations in August and data from previous studies. The second theory concerns the place of formation. Carbon dioxide has a lower condensation temperature than water. In the protoplanetary disk, there is a boundary called the carbon dioxide ice line. Inside this line, carbon dioxide remains in a gaseous state, while outside it condenses into solid ice. The line of water ice is closer to the star. If the Three-Aya Atlas formed beyond the line of carbon dioxide ice in a disk with unusually high carbon content, it could naturally incorporate more carbon dioxide than water during its formation. This ratio is recorded in the comet's composition from the very beginning. This theory requires specific conditions. A protoplanetary disk with a high ratio of carbon to oxygen, or a disk where the temperature gradient has placed a forming comet in a zone rich in carbon dioxide ice but poor in water ice. Both scenarios are possible. The metallicity of stars varies, the structure of disks is also different, but finding conditions that would ensure an 8-to-1 ratio is not easy. Fine-tuning is necessary. A star system is needed that significantly differs from ours in aspects that should be rare, but not impossible. Observations from SphereX since mid-August provide additional confirmations of this theory. A space infrared telescope detected a massive cloud of carbon dioxide stretching at least 348,000 kilometers from the comet's core. No water cloud was found at similar scales. Carbon dioxide escapes faster, moving outward and dominating the comet's structure. At the same time, water production remained below detection limits for SphereX with an upper limit of about 4.5 kilograms per second. This is an order of magnitude less than the rapid detection of 40 kilograms per second, which itself raised doubts considering the distance and methodology. This discrepancy indicates an important point. Detecting water is difficult. It requires specific wavelengths and specialized instruments. SWIFT detected hydroxyl, a decomposition product, rather than water itself. SphereX searched for water emission lines in the infrared range and found none. JWST discovered water, but in smaller quantities than carbon dioxide. Each telescope sees its part of the puzzle. Coordinating their data requires assumptions about the chemistry of the coma, rates of photodissociation, and spatial distribution. None of these assumptions have enough certainty for an interstellar comet with an unknown composition. One detail from the JWST data is that the water emission at a wavelength of 2.5 micrometers shows spatial structure. It is not evenly distributed in the coma. There are bright and dim areas indicating localized sources, possibly jets or regions rich in water, ice mixed with dominant carbon dioxide. When these areas are exposed to sunlight, they release water in bursts rather than through uniform sublimation. As a result, the spectral maps appear mottled. The emission of carbon dioxide at a wavelength of 4.5 micrometers is smoother and evenly distributed, corresponding to large-scale sublimation across the sunlit side of the comet. This spatial difference is significant for the structure of the comet. If the three eyes of the atlas form a homogeneous mass consisting only of carbon dioxide, then the gas plume should be uniform. The fact that the water shows localized emissions suggests heterogeneity, with pieces, layers, or sections of different compositions mixing, like a geological formation with clear layers, each capturing different epochs of the comet's formation or evolution. As the surface erodes, various layers are revealed, and gas production changes accordingly. However, there is an alternative interpretation. Localized water emission may originate from an icy debris field in the coma, the same pieces that SWIFT indirectly detected through hydroxyl. If these fragments have a different composition than the core, for example, some rich in water and others in carbon dioxide, then spatial variations become understandable. You do not see the structure in the core. You observe the structure in the cloud around it. Hundreds or thousands of icy fragments, each a miniature comet, each contributing to the overall glow in varying proportions. To distinguish between these interpretations, a more detailed image is required. It is necessary to resolve the comet's nucleus, to find out if there are active zones or jets, or specific holes releasing gas. The Hubble telescope cannot do this as the nucleus is too small and too far away. JWST will also struggle because its field of view is too narrow and the comet is moving too quickly for detailed mapping. Perhaps the JWST spacecraft will be able to do it in November if the comet is bright enough and close enough, and the cameras can track it. But that is still uncertain. The detection of carbon-sulfur gas, though preliminary, adds another layer. OCS is not common for comets in the solar system. It appears only rarely, and typically, in small amounts. Its presence indicates the existence of sulfur chemistry in the protoplanetary disk. If 3I Atlas detected measurable OCS, it indicates that the parent star had sulfur during the planet formation period. In combination with the dominance of carbon dioxide, we build a picture of a star system with unusual ratios of volatile substances, high carbon and sulfur content, low oxygen, or at least less water, a system where chemistry leans towards reduced compounds rather than oxidized ones. Why is this important? Because volatile chemistry determines the possibility of life. A star system rich in carbon dioxide and sulfur, but poor in water, is not conducive to life as we understand it. Water is a universal solvent, the medium where biochemistry occurs. Carbon dioxide is beneficial. Plants use it for photosynthesis, but it cannot replace water. If the 3I Atlas formed in a system where water was scarce, any planets in this system would face serious challenges in developing or maintaining biology. These will be dry worlds, rich in carbon but poor in water. Such planets we have begun to find around red dwarfs, those small stars that numerically dominate the galaxy. Is such a system the source of the 3I Atlas? A red dwarf system where the habitable zone is close to the star, tidal interactions heat one hemisphere while freezing the other, with insufficient water and a carbon dioxide-dominated atmosphere. The origin from a dense disk supports this hypothesis. Old stars, on average with low metal content but with wide variations, red dwarfs formed 10 billion years ago and still glowing, while the planets around them evolved or did not evolve under harsh conditions. This is speculation, filling in gaps with overlapping assumptions, but chemistry doesn't lie. 7.6 to 1. This is not a random number, it's a constraint, a condition that any model of formation must meet, requiring either extreme processing over billions of years or formation in an environment fundamentally different from the one that gave us Earth. Observations by the JWST concluded in August. The comet came too close to the Sun for safe observation, and the telescope switched to other targets. There are no plans for subsequent observations after perihelion. The time of the James Webb Telescope is extremely valuable, reserved months in advance, and the window for observing the Comet 3 Eyes of Atlas has already closed. No matter what happens on perihelion, whatever changes in chemistry occur during maximum solar heating, we will not be able to see it through the Webb. We rely on data from the JWST spacecraft and ground telescopes to capture the consequences, and by that time, the ratio of carbon dioxide to water could have changed. The chemistry of the comet may have evolved, and the evidence captured by the Webb in August could be the only snapshot of the Comet 3 Eyes of Atlas in its state before perihelion. This makes the data indispensable, a chemical imprint of an object formed in another star system billions of years ago, a record of volatile substances reflecting conditions we cannot reproduce or observe directly, and a mystery that deepens as we analyze it. Comet 8.1 is not just unusual, it is a marker indicating that something has occurred here that does not happen in our corner of the galaxy, whether natural or artificial, accidental or planned, a question that does not give peace. Chapter 5. Mars witnesses the visit October 3, 2025. The three-eyed Atlas comet streaked past Mars at a distance of 29 million kilometers. For context, this is about 77 times farther than the distance from the Earth to the Moon, which is considered a close distance in cosmic terms. Close enough for the European Space Agency's orbital spacecraft, designed to photograph rusty rocks from hundreds of kilometers above, to aim their instruments upward and capture the interstellar visitor as it raced through Martian space at 67 kilometers per second. The orbital device ExoMars Trace Gas captured the best images. The gaseous color and stereoscopic imaging system recorded a series of exposures from October 1 to 7. The image does not impress by Hubble standards. 3 eyes of Atlas appear as a blurred white dot, slightly elongated, moving against a backdrop of star streaks. The streaks are formed because Cassius tracked the comet, compensating for its movement relative to the spacecraft. Each exposure lasted 3 minutes. By combining them, one can achieve a rough animation where a point descends down the frame. The coma is clearly visible as a diffuse halo several thousand kilometers wide. There is no tail, at least none whose brightness exceeds the noise threshold. Nick Thomas, the lead researcher of the Cassius system, acknowledged that the observation was challenging. The comet is about 10,000 to 100,000 times dimmer than our usual targets. And the target is Mars, a planet reflecting sunlight up close. Setting the same camera on a dim comet 30 million kilometers away is like using a microscope to examine the horizon. The tool was never meant for this. The exposure time was incorrectly chosen, sensitivity on the edge of acceptable, but they managed. A small number of pixels, a spot of light. Confirmation that the Comet 3 Eyes of Atlas was exactly where orbital mechanics predicted, knowing precisely what the comet does as it approaches the Sun. Mars Express, one of the 2 orbital spacecraft of the European Space Agency, attempted to conduct observations, but the comet turned out to be too dim. The high-quality stereo camera yielded no results. The Amiga and SpyCam spectrometers searched for spectral signatures, but the signal-to-noise ratio was too low for reliable detection. Perhaps they managed to capture something, a barely noticeable emission line, or a subtle absorption feature. But the data remains ambiguous, at best preliminary. The real value of Mars Express lies in the contextual geometry. Knowing the exact position of the spacecraft, the time of observation, and the field of view gives us constraints. If 3 objects from the Atlas released smaller fragments during flight, if pieces separated from the core, Mars Express should have seen them. The fact that it recorded nothing but the main object indicates that fragmentation has not yet occurred. The comet remained intact. NASA's Martian orbiters were also on guard. The Mars Reconnaissance Orbiter, equipped with a high-resolution camera, has the capability to directly capture the core if the geometry aligns favorably. At a closest approach distance of 29 million kilometers, the resolution is about 30 kilometers per pixel. Considering that the core was estimated to be 5 to 6 kilometers, it would appear almost as a single pixel, looking like a burst of brightness, one overexposed pixel surrounded by a dim halo. However, it should be detectable if the exposure settings were correct and the direction precise. At the time of recording, no high-resolution images had been published, but this is not unusual. Processing data from Martian orbiters takes time. Images accumulate, are transmitted when bandwidth allows, go through calibration processes, and eventually end up in public archives. A delay of several months is a normal occurrence, but the lack of immediate data release fuels rumors. Some corners of the internet insist that NASA is hiding information, that the Mars Reconnaissance Orbiter saw something unexpected, and the images are being analyzed privately before any public statement. This is complete nonsense. NASA operates differently. Martian missions are public programs with a data release policy, and everything eventually becomes publicly available. The delay is due to operational reasons, not a conspiracy. Nevertheless, speculation highlights something important. People are paying attention. 3 objects from the Atlas captured the public imagination more than any of the IU Muramura devices or the 2 Iberos. Perhaps it was the timing. Perhaps the provocative theories of Leob created a narrative foundation that science fiction fans could latch onto. Or perhaps social media is simply more mature now and better able to elevate niche topics to a level of broader awareness. Regardless, the flight of October 3rd became not only an astronomical event, but also a cultural moment. People who had never looked through a telescope suddenly became interested in orbital mechanics, spectral analysis, and the difference between a comet and a technological artifact. Perseverance, NASA's rover, also conducted observations in Jezero Crater. The mass cameras and Z can capture objects in the Martian sky, stars, Phobos, Deimos, and the Sun during eclipses. Theoretically, they could record Comet Tri-I Atlas if it were bright enough and high above the horizon during the rover's working hours. On October 1st, several images from cameras captured a faint streak in the sky. Simon Schmoose, an astrophotographer, processed these images by layering them and enhancing the contrast. The result shows a blurred spot in the location where the orbital model predicted the comet Tri-I Atlas. This is not definitive proof. It could be a trace of a cosmic ray or image compression artifacts, but the position and time match, and if this is indeed the case, then this is the only photograph of an interstellar object ever captured from another planet. Avilo published about this, using as evidence that the comet can be tracked and observed with existing tools if simply pointed in the right direction. However, some were skeptical about this. The streak is too weak and vague. Extraordinary claims require extraordinary evidence, and the blurred spot and overlaid image do not meet this criterion. Nevertheless, the discussion itself is valuable. It compels people to engage with data, critically reflect on what constitutes evidence and what is possibility, and confront the uncertainty that defines the boundaries of discovery. The Chinese Tianwen mission and the UAE's Hope probe were also near Mars during the flyby. Both spacecraft are equipped with cameras and spectrometers and could theoretically observe Comet Tri-I Atlas. However, no data from either mission has been published yet. The Taiwanese mission operates under different data exchange protocols than NASA or ESA. Images and results are published through scientific articles and press releases on timelines that do not align with Western expectations. Hope is more transparent, but its main task is to study the atmosphere rather than observe deep space. If any of the devices recorded useful data, we will find out later, but silence is not proof of absence. It is simply the nature of international space exploration, where coordination is imperfect and priorities differ. The flyby of Mars was always planned as a brief moment, a small window when the geometry aligned and cameras could quickly look up at the sky before returning to their main tasks. But this moment confirmed important details. The comet Tri-I Atlas was intact, its coma active and visible, its orbit matching predictions despite measurement errors. No fragments or secondary objects, no signs of anything except one comet on a hyperbolic trajectory doing what comets do. Except for one moment that no one speaks about publicly, but everyone thinks about privately. The coma was larger than expected. Based on the sunlight flow at this distance and the estimated nuclear size, the coma should have a diameter of about 2 to 3,000 kilometers. Images from Cassius suggest it spans 4 to 5,000 kilometers, which is not a large margin of error. These estimates are generally very uncertain. Everything depends on exposure time, detector sensitivity, and how you define the boundary between coma and background. But it is larger than models predict. It is larger than it should be if the gas ejection speed is proportional to solar heating. Why is it larger? One explanation is that the comet's core is more active than previously thought, and 8% of its surface may be an underestimate. Every 10 or 12% of the surface releases volatile substances, creating a larger coma than predicted. Another explanation is the contribution of the icy debris field. These pieces, floating in the coma, each sublimating independently, increase the effective size of the gas emission area beyond the core itself. The third explanation, which no one wants to speak aloud but often arises in private conversations, is that the 13th Catalyst mission did something on Mars, released material, and dropped gas, which could have led to a temporary increase in coma production. There is no evidence for the third explanation, absolutely none. But the absence of evidence is not evidence of absence, and the flyby past Mars was the last clear observation before perihelion. If something was meant to happen, if the probes were to unfold or break apart, or if the comet transformed from a dormant state to an active one, then the flyby window was the logical moment. Close enough to the planets to be interesting, yet far enough from the sun for maneuvers to remain effective, hidden from direct observation from Earth, but observable by spacecraft on Mars. The fact that the Mars orbital probe saw a normal comet with a slightly enlarged coma brings both reassurance and disappointment. Reassurance because it meets expectations. Disappointment because the slightly enlarged coma is ambiguous enough to support multiple interpretations without confirming any of them. There is another data point from Mars that has not yet been fully analyzed. The Nomad spectrometer on the Trace Gas Orbiter not only captured an image of the 13th comet Atlas, but also obtained spectra. Although they are low resolution and heavily contaminated by scattered sunlight and instrument noise, they are still spectra. These observations are still being processed. The team is working on calibration issues, trying to extract a signal from data that was not originally intended to capture such a dim and fast-moving object. If they succeed, if Nomad can capture the spectral lines from the coma during the flyby, we will obtain data on the composition from a completely different perspective than JWST, Hubble, or Sphere X. Different geometries of observation, different angles of phases, different lighting conditions. Any molecules that appear in the Nomad data can be matched with previous observations. Any missing molecules that should be present will become interesting. Results will not be obtained quickly. Spectral analysis is a meticulous task, months of effort to extract meaningful scientific data from marginal data. But the team is motivated. This is the type of observation that defines careers. A once-in-a-lifetime chance to study an interstellar comet from Mars's orbit during its closest approach. If scientists extract useful data from these noisy spectra, the wait will be justified. Mars also provided something else, a test of tracking and coordination protocols. Ray Atlas moved quickly, 67 kilometers per second relative to the Sun, though slower relative to Mars due to orbital mechanics. Aiming a spacecraft's instrument at a moving target requires precision, real-time updates, and perfect timing. Mars's orbit accomplished this. Cassius captured the comet right in the center of the frame, and this success confirmed the methods. This proves that we can coordinate observations from multiple spacecraft and agencies, targeting an object that does not give us a second chance. This matters for November. When JWST observes after perihelion, coordination will become even more critical. The comet will be brighter, but also more active, potentially fragmented and changeable. JWST will require accurate information, updated in real time based on ground observations and orbital calculations. The flyby of Mars was a dress rehearsal. JWST is the main event, and everything learned from the observations of October 3rd, each targeting procedure, calibration method, and data processing will be applied to make the November observations as scientifically productive as possible. The Tri-Eye Atlas has already left Mars. The geometry has changed. The comet moves deeper into the inner solar system, closer to the Sun and further from the red planet. Orbital probes return to their usual tasks, mapping surface features, analyzing atmospheric composition, searching for subsurface water. A brief distraction from the interstellar visor passed, and Mars became just Mars again, solitary in its orbit, awaiting the next close encounter with something from beyond. Chapter 6. Will it crumble? The fragmentation of comets is not uncommon. It's not particularly unusual. Dozens of comets have disintegrated throughout recorded history, some spectacularly, some quietly, but all follow a pattern that astronomers understand quite well. Thermal stress breaks apart the nucleus. Exhaust gases create internal pressure. Rotation and tidal forces tear apart loosely bound materials. The comet that was becomes a comet cloud that was, and we document it, analyze it, adding it to the catalog of objects that could not survive perihelion. The Tri-Eye Atlas is not required to survive. This must be made clear. This is an object held by gravity so weak that you can leave it with a quick step, an object that has undergone thermal cycles between nearly absolute zero and the heat it has experienced over billions of years wandering through the galaxy. The object is porous and cracked, full of voids where volatile substances once were before they vanished during previous encounters with stars, about which we know nothing. The structural integrity is questionable, cohesion is minimal, and the force holding the core together is measured in newtons rather than megatons. The question is not whether the comet Three-Eyed Atlas will break apart, but whether it will actually happen. The answer depends on factors that we cannot measure from Earth. Let's start with historical examples. Comet Shoemaker-Levy 9 is a well-known case discovered in 1993, when it had already broken into more than 20 separate fragments, stretched along its orbit like beads on a string. The destruction occurred in 1992 during a close flyby of Jupiter. The tidal forces exceeded the strength of the comet, and the core shattered. By the time we noticed it, the fragmentation was complete. 18 months later, fragments collided with Jupiter in a series of impacts, leaving dark marks visible for several months. The largest fragment released energy equivalent to 6 million megatons of TNT. And this is not due to chemical explosives, but exclusively from kinetic energy. Physics does not care about your comfort level. However, Shoemaker-Levy 9 was a small, loosely bound comet of Jupiter's family, already weakened by previous orbital passes. The Three-Eyed Atlas is larger, denser, and this is its first and only passage through the inner solar system. Other circumstances mean other risks. The Three-Eyed Atlas comet broke apart during its appearance in 1995, and then again in 2006. Each passage led to particles separating. By 2011, observations recorded over 60 separate fragments, most of which were tiny, but all followed similar orbits, slightly offset due to the speed gained at the moment of separation. The core still exists, still moves in orbit, but weakened and shattered. It accumulated mass with each perihelion until ultimately nothing remained but a stream of debris, a meteor shower that will occur when Earth crosses this orbit in centuries. Comet C 2019 Y4 is confusing because part of its name coincides with the Three-Eyed Atlas, but it is completely unrelated. It broke apart in April 2020, approaching its first perihelion, expectedly brightening, and causing excitement among astronomy enthusiasts who thought it might become visible to the naked eye. Then it began to quickly fade. In just a few days, it transformed from a compact core into a cloud of fragments too small to distinguish. The Hubble image shows the rupture. The fragments scattered and disappeared. The comet ceased to exist as a whole object. No one knows why C in the year 2019 disintegrated. It was not close to the sun, tidal forces were insignificant, and the rotation was not extreme. The best guess is thermal stress. Rapid heating on the sunlit side with a frozen night side caused differential expansion, and the core cracked. As soon as the crack appeared, gases escaping from the freezing ice exploited this weakness. The gas pressure caused the crack to widen. The process accelerated, and within hours or days, the structural failure became catastrophic. Did this happen to the Three-Eyed Atlas? Certainly. The thermal gradient at perihelion will be extremely sharp. One side will be scorched by direct sunlight, while the other remains in shadow, cold, and almost untouched. The temperature difference can reach hundreds of Kelvin over a core just 5 to 6 kilometers in diameter. This creates ideal conditions for mechanical stress. Add to this the internal pressure from the sublimation of carbon dioxide, which occurs explosively at the temperatures that the Tri-Ain Atlas will experience, and we have all the components for a destructive event. However, there is a counterargument. The three-eyed Atlas has been active for several months, at least since June, when previous images show a faint comet. The comet is releasing gases, gradually reducing pressure and blurring its surface. This slow erosion can actually prevent catastrophic destruction. It can be imagined as a pressure relief valve. As long as gas can evenly escape through surfaces and cracks, internal pressure does not reach dangerous levels. The comet is losing volatile substances at a controlled rate, decreasing its mass while maintaining structural integrity. The rotation period also supports this theory. 16 hours and 16 minutes is a stable figure that neither increases nor decreases. If sublimation occurred unevenly, if the gas jets acted asymmetrically, we would observe changes in the rotation speed, as such jets would impart torque to the core. The fact that the rotation remains constant indicates balanced gas release and symmetrical erosion. The core does not disintegrate under its own activity. Moreover, large comets have the advantage of size. They are harder to fragment. Gravity is proportional to mass, while tensile strength relates to cross-section. For an object 5 kilometers in size, even if it consists of loosely bound ice and dust, gravity prevails. The escape velocity is only a few meters per second, but this is enough to hold the debris together against rotation and moderate sublimation. A significant impulse is required to overcome this binding energy, a powerful burst, collision, or tidal interaction that the Three-Ain Atlas will not experience unless the core is already damaged and is a loose mass held by friction rather than cohesion. In this case, even minimal tension can lead to separation. The fragments will not scatter with fury. They will drift slowly apart, as their slightly different orbits cause separation over days and weeks. From a distance, it will look as if the comet is melting away. The core will become less distinct, the coma will take on an asymmetric shape, and eventually several condensations will appear, separate peaks in the brightness distribution. Each fragment will follow its trajectory, close but not identical to the original orbit. Yes, as shown by the ExoMars images from October 3rd, at that moment, there were no signs of fragmentation. The core appeared as a single concentration of brightness, but the resolution was weak. If fragments had separated by only a few kilometers, Cassius would not have been able to distinguish them. They would still appear as one indistinct object. The only way to confirm the integrity is to conduct high-resolution imaging after perihelion, and this is a task for JWST. Now let's consider an alternative interpretation of LIOP. What if the fragmentation is not random? What if this is done on purpose? A mothership reaching perihelion and releasing mini-probes appearing at a distance identical to a comet breaking apart under thermal stress. We see many objects where there was once one. We observe them moving along different trajectories. We see how the brightness of fragments changes as they rotate and present different sections to the sun. All of this can be explained by natural processes, but it can also be explained by intentional deployment. The difference lies in the details. Natural fragments follow ballistic trajectories, their orbits determined by the speed of their separation and the gravitational field they move through, allowing us to predict their locations based on Newtonian mechanics with no surprises. At the same time, the deployed samples can maneuver. They have a propulsion system that allows them to change their trajectory after separation. If fragments appear that do not follow predicted ballistic paths, if they accelerate or decelerate or change direction, it is a techno-signal, unequivocal and final. Lieb called it the dandelion hypothesis. The mothership disperses seeds, each seed equipped with sensors and communication devices. The biological analogy is not coincidental. Dandelions do not place their seeds neatly. They scatter them in the wind, relying on quantity rather than precision. Most seeds fall on poor soils and perish. Only a few find favorable conditions and thrive. For a technological civilization exploring the galaxy, the strategy is similar. Release hundreds of probes. Most will fail or find nothing interesting, but some will be able to collect data and return with it. The cost of each sample is low, but the potential profit is enormous. If 3 Ayatlu follows this model, Perihelion is the moment of deployment. Samples are launched. They use the sun's gravity and their own propulsion to reach target planets: Earth, Mars, Venus, possibly even Europa and Enceladus if the mission profile includes exploring icy moons. Each sample has a specific purpose and enough fuel to reach it. For several weeks or months, they arrive, begin observations, and send data back to the mothership before it leaves the solar system and goes beyond the communication radius. From our perspective on Earth, we observe as if a comet is breaking apart. We analyze fragments, calculate their orbits, publish articles on thermal effects and structural damage, and miss the real story unfolding before our eyes because we assume natural processes while something else is happening. This is indeed a nightmarish scenario for Lioba. It's not that 3-Iotl were technological, but that they are technological, and we misinterpret the evidence because we do not seek the right signals. We have spent centuries studying comets. We know how the fragmentation of comets looks, and this knowledge influences our interpretations. When we observe fragments, we assume that the cause is something natural. Overcoming this bias requires conscious effort, active searching for anomalies, and more careful tracking of fragments than in the case of ordinary comet destruction. We seek changes in trajectory, events related to motion, anything that deviates from ballistic movement. This software automatically performs some of these tasks. The spacecraft tracks moving objects, calculates anomalies. If a fragment moves differently than predicted, the program signals this. However, the software expects minor deviations due to gas emissions rather than significant course changes related to movement. The threshold for detecting anomalies is set for natural objects. It is unknown whether this threshold is sensitive enough to catch the deployment of the probe. No one has tested this. No one needed it. There is another consideration. If the 3 Eyes comet breaks apart naturally or artificially, we will lose the main object. The fragments are less bright and harder to track. Spectroscopy becomes a more complex task as the signal is distributed among several objects. The ability to study and preserve the comet's core disappears. From a purely scientific perspective, destruction is the worst outcome. This means we do not get pure data on composition, structure, and density. We receive a cloud of debris, interesting in itself, but not the perfect sample we hoped for. However, if it remains intact, if the 3 Eyes comet survives perihelion as a single cohesive object, we will obtain this sample. The JWST probe observes it in November. Ground telescopes capture it in December. We track its movement past Venus, past Earth's orbit, towards the asteroid belt, and beyond. We observe how it dims as distance and decreasing solar heating halt the gas outflow. We document the evolution of the tail, the dispersion of the coma, the return to a state of rest. And we study everything we can before it crosses Jupiter's orbit in March and disappears forever. So the question remains, will it break apart? The answer will be known in November, when JWST gets its first clear view after perihelion, when we will see if the 3 Eyes comet remains a single object or has broken into many, whether the core has survived or shattered. Will this story end in a quiet disintegration of fragments or continue with an intact comet carrying its secrets into the darkness beyond? Chapter 7. A Decade-Long Journey. Xavier Perez, Couto, and his team from the Acarina University traced the trajectory back. 10 million years of orbital integration using Gaia data on the positions and velocities of stars. They searched for close encounters, stars that could disturb the 3 Eyes comet during its long drift through the galaxy, stars that could indicate its origin system. However, instead, they found something more disturbing. Nothing disturbed her. 93 potential star collisions were identified. 62 of them were classified as highly reliable, and none of them significantly altered the comet's trajectory. Consider what this means. 10 million years of travel through the galactic disk, through regions filled with stars, clouds of dust, molecular complexes, through spiral arms where stellar density peaks, and gravitational interactions become inevitable. And so the 3-eyed Atlas pierced through all of this, practically unscathed, like a bullet. 60 kilometers per second relative to the local standard of rest. Too fast for gravitational wells to capture it. Too massive for radiation pressure to deflect it. Just inertia propelled him forward along a trajectory that remains virtually unchanged over timescales, exceeding the age of human civilization. Speed is the key point. The 3-eyed Atlas moves at 58 kilometers per second in the galactic reference frame. For comparison, the Sun rotates around the galactic center at a speed of about 220 kilometers per second. Most stars in the vicinity of the solar system move at similar speeds, plus or minus 20 or 30 kilometers per second. The three-eyed Atlas does not just move. He moves differently. His velocity vector does not match the local flow. He does not participate in the organized rotation of the galactic disk. He crosses this rotation at a steep angle, indicating his origin from another place, from a place with different kinematics and orbital properties. The thick disk is an obvious candidate. This population of ancient stars is squeezed between the thin disk, where the Sun is located. The stars of the thick disk formed in the early history of the galaxy when the Milky Way was smaller, more chaotic, and less organized into the neat spiral structure we observe today. They all move at higher speeds perpendicular to the galactic plane. They dive up and down through the disk instead of staying within its bounds. Their metallicity is generally lower, as they formed from gas that has not yet been enriched by several generations of supernovae. Matthew Hopkins and a team from Oxford conducted simulations, modeling a population based on galactic structure and dynamics. Their findings, published in a preliminary version shortly after the comet's discovery, suggested a 2/3 probability that the three-eyed Atlas originated from a thick disk. Not uncertainty, not proof. Just statistical probability based on trajectory analysis and speed comparison. But 2/3 is a high degree of confidence in astrophysics. High enough to build hypotheses. High enough to start making predictions. If the three-eyed Atlas is indeed from the thick disk, then it is ancient. The thick disk stopped forming stars about 10 billion years ago. Any comet ejected from the planetary system of the thick disk has wandered for most of the current age of the universe. Our solar system has existed for 4.6 billion years. The three-eyed Atlas may be twice as old. It could have formed when the universe was less than 4 billion years old, during the era when the rate of star formation peaked in all galaxies. And the cosmic landscape looked completely different than now. 10 billion years of influence on the interstellar environment, 10 billion years of cosmic impact. Galactic cosmic rays, energetic particles accelerated by shock waves from supernovae and active galactic nuclei, strike the surface of a comet at relativistic speeds. Each strike releases energy, breaks chemical bonds, dislodges atoms, and over geological timescales, damage accumulates, surfaces erode, chemistry changes, and the crystalline structure becomes amorphous. What initially was pure ice from the protoplanetary disk transforms into a material subjected to radiation processes, barely resembling its original composition. Except for what lies deep within, cosmic rays penetrate only to a certain depth. The stopping distance for a typical galactic cosmic ray, a proton, in ice, is measured in meters. For particles with the highest energy, this distance is tens of meters, but a core with a diameter of 5 kilometers has sufficient protective depth. The inner layers, protected by overlaid layers, remain untouched, unchanged, like a time capsule preserving the chemistry of the star system formed in the youth of the Milky Way. This is what makes Comet 3I Atlas scientifically invaluable. She is not just old, she is a direct sample from the early galaxy, a piece of a protoplanetary disk that condensed into a comet while the thick disk was still actively forming stars. Everything we know about this era is based on indirect observations, such as distant galaxies showing what the universe looked like billions of years ago. Stellar archaeology in the Milky Way, where we analyze the chemistry of old stars to understand what the interstellar environment was like at the time of their formation. Computer simulations of galaxy evolution reproduce observed properties but have huge uncertainties. The Comet Atlas is a physical artifact, not a simulation. A real object we can point telescopes at. An object carrying chemical signatures captured during its formation, isotopic ratios, organic molecules, crystalline structures in ice. This preserves information about conditions in that primordial protoplanetary disk. The ratio of carbon dioxide to water becomes more significant in this context. A 1-to-1 ratio is not just unusual. It is a constraint for the environment of formation, indicating that the parent star system had specific properties. A high carbon content compared to oxygen or a temperature gradient in the protoplanetary disk that placed the comet formation zone beyond the line of icy carbon dioxide, but in a region where carbon was unusually available. These conditions may be widespread in thick disk systems or may be rare. We have no statistics. AI Atlas is our first comet from the thick disk, with a sample size of 1, but 1 is much better than none. Before the discovery of 3 Atlas, all we knew about the populations of planetesimals in the thick disk was theory. Models predicted that these ancient star systems ejected comets and asteroids just like modern systems. It is assumed that some of these objects will wander through the galaxy for billions of years, and statistically, one of them will inevitably pass through our solar system. The three-dimensional atlas confirms these assumptions, validates models, and proves that the early galaxy formed planets and comets, participating in the same dynamic processes that characterize star systems today. The trajectory analysis also revealed something subtle. The three-dimensional atlas moves almost perpendicularly to the plane of the galaxy. Its speed component in the z-axis direction, that is, out of the plane, is unusually high. This is characteristic of thick disk objects, but it also means that the comet has been oscillating up and down through the galaxy for billions of years. Each oscillation takes tens of millions of years, rising through a thin disk, emerging into the galactic halo, returning through the disk, and rising again along a sinusoidal trajectory that carries a three-dimensional atlas through vastly different conditions throughout its existence. Sometimes he finds himself in dense areas of the disk, where star formation is active, and the frequency of supernovae is high. The level of radiation peaks, the number of impacts with dust increases, and the comet disintegrates faster. Sometimes she finds herself in a halo, in the almost empty space between galaxies, where radiation levels drop and impacts become rare. The comet becomes inactive. Erosion slows to nearly zero. This cycle between harsh and favorable conditions may explain why the three-dimensional atlas has survived for 10 billion years. Phases in the halo allowed it to rest, halt mass loss, and preserve its internal composition from the relentless destruction of interstellar travel. Shock groups conducted a comparative analysis. Oumuamua, Borisov, and the three-dimensional atlas. 3 interstellar objects with completely different origins. Oumuamua from a thin disk, young, possibly 1 billion years old. Borisov, intermediate, about 1,700,000,000 years old, also from a thin disk. And the three-dimensional atlas, ancient, with an average age of 4,600,000,000 years, but potentially much older from a thick disk. The diversity is astonishing. It tells us that interstellar objects are not a uniform population. They come from everywhere, of all ages, from all regions of the galaxy, each carrying its own story. And if such diversity exists for the 3 objects we discovered, imagine what the entire population looks like. When the Vera Rubin Observatory becomes fully operational, it is expected to detect dozens of interstellar objects a year, perhaps even more. Each of them will have their own story, origin, and trajectory through the galaxy, which can be traced through modeling. We will create a census and map the distribution of ejected planetesimals across the Milky Way. We will also determine which types of star systems are most effective at ejecting material into interstellar space and which regions of the galaxy contribute the most to the wandering population. The three-eyed atlas is the path of the explorer, an object that demonstrates our capability for such archaeology. We can take a comet discovered in July and by October form a reasonable hypothesis about where it came from and its age. The uncertainty is vast, spanning billions of years, but the methodology works. Integrating orbits, modeling populations, and chemical analysis create a history of origin. Imperfect, yet improvable. There is another assumption mentioned by Parascuto, but he does not emphasize it. If the three-eyed atlas traveled for 10 billion years, he visited other star systems, many other star systems. The galaxy spins, stars move, and in 10 billion years, a comet passed within a few light years of thousands or millions of stars. Some of these stars had planets, some of the planets could have life, and the three-eyed atlas flew unnoticed or ignored through these systems, carrying ancient ice to the next encounter. This raises a question that no one wants to ask directly. If three-eyed atlas visited other civilizations, if he passed through their solar systems just as he does through ours, what happened? Did they notice him? Did they study him? Did they ignore him as just another comet? Or did they do something else? They left a mark, attached a probe, using it as a relay for communication over interstellar distances? We have no evidence of this. None. But the lack of evidence is not decisive when it comes to events that could have happened a billion years ago, around stars that we cannot even identify. The three-eyed atlas can carry messages, data, technologies, things left by civilizations that rose and fell while the Earth was still a molten sphere of rocks, and we would not know about it if we did not look closely and with intent, ready to consider possibilities that seem absurd until you start comparing timescales and realize that absurdity does not equal impossibility. 10 billion years is a long time, enough for empires to rise and fall, for species to develop intelligence, and then perish, enough for entire star populations to be born and die. Three-eyed Atlas traveled through all this, remaining a silent witness to galactic history, and now, for a few short months, it is here, passing through our system, offering us the only chance to read the story it carries in its chemistry and structure, and perhaps in changes we have yet to discover because we have not sought them. The trajectory continues, past Jupiter and Mars, then beyond the asteroid belt, past the heliopause, where the solar wind gives way to the interstellar medium, back into darkness, back into infinite drifting between stars. 10 billion years have already passed, 10 billion more ahead, until the galaxy itself changes beyond recognition, and the three-eyed Atlas will still be there, moving, carrying its secrets, waiting for the next civilization to notice it. Scientists react sharply to recent questions, with Tom Stetler, NASA's leading expert on small bodies of the solar system, directly addressing the hypothesis of a technological artifact during a press briefing. His answer was unequivocal. It looks like a comet, behaves like a comet, and strongly resembles all known comets. The emphasis on the words, very, very, was intentional. It was not a diplomatic evasion. It was a statement from a scientist who drew a clear line and said, enough. Disappointment in the astronomical community is palpable, not because questions are being asked. Questions are important. They form the basis of science. But because these questions are exaggerated, low-probability hypotheses receive as much attention as substantial evidence of natural origins, and every new observation, spectrum, and image must pass through a narrative of extraterrestrial probing before true science can be discussed. Chris Lintotter Doxford was even less diplomatic, calling the technological hypothesis absolute nonsense on a stick, an insult to the exciting work aimed at understanding this object. Lintott was part of the team that traced the path of Atlas's three eyes back to the thick disk. He spent months analyzing data on trajectories, conducting population simulations, and publishing results that deepen our understanding of galactic dynamics and the origins of interstellar objects. And then he observes how these results are drowned under headlines about extraterrestrial motherships and mini-probes. The scientific community's investments in rigorous analysis are overshadowed by speculations that require no evidence and provide no verifiable predictions. Jason Wright from the University of Pennsylvania chose a different approach. He wrote a detailed blog post, systematically analyzing each of the stated anomalies, point by point, dataset by dataset. Wright is not opposed to researching technosignatures. He works in this field and is part of a community seeking evidence of extraterrestrial intelligence. But he is also a meticulous scientist who insists on adhering to standards, and by those standards, Atlas's three eyes fail every test. Not due to brightness issues, the claim that early observations showed an object 20 kilometers in size suggests it must be something else. Wright points out that this is a selective representation of data. Early observations were low resolution, made when the comet was faint and distant. As the tools improved and exposure time increased, the size estimates converged on 5 to 6 kilometers. This is normal refined observability, not a mystery requiring exotic explanations. What about the claim of missing tomography signals in early spectra? Wright delved into these articles. The observations were on the edge. The signal-to-noise ratio barely exceeded the detection threshold. The absence of clear molecular lines was not evidence of an unusual composition. It was proof that the comet was too weak for definitive spectroscopy at such a distance. When the James Webb Space Telescope and other important instruments began to operate, characteristic signatures became visible. Water, carbon dioxide, carbon monoxide, carbonyl sulfide, all of which are exactly what one would expect from a comet. The initial uncertainty was related to observational limitations rather than physical reality. A trajectory probability of 0.5 thousandths percent? Wright independently conducted calculations, which heavily depend on the definition of a close approach. If realistic detection thresholds are used, considering that we can only see objects exceeding certain brightness levels, the probability increases significantly. You do not calculate the chances of any random object passing by 3 planets. You calculate the chances that an object bright enough for detection will pass near 3 planets, and this is already a significantly less strict condition. The probability remains low, but not absurdly low, not anomalously equal to 5 sigmas. Then the question of dust configuration arises. The assertion that dust ejection towards the sun requires active propulsion or ventilation. Wright refers to decades of comet science, showing that dust distribution is complex. Jet activity is never uniform. The orientation of the rotation axis is crucial. Local changes in the content of volatile substances create asymmetric emissions. The specific pattern observed in the Comet 3I Atlas may be unusual, but it fits within the bounds of natural behavior. Dozens of comets in the solar system exhibit similar features. No one assumes alien technologies to explain them. The argument about the rotation period loses meaning upon deeper analysis. 16 hours and 16 minutes is remarkable for a comet of this size. It is a stable indicator that will not lead to destruction. It aligns with both a loose cluster and a solid object. This says nothing about artificial or natural origins, as both options could have similar rotational dynamics. Using this as proof of technology means claiming that the stone is artificial because it is round. Roundness can be natural or created. The period of rotation can be either natural or designed. The measurement itself is neutral. Wright calls his sharpest criticism of the argument about the direction of approach. The claim that moving from the constellation Sagittarius toward the galactic center is tactically wise to avoid early detection is an attempt to impose intention on geometry. The three-eyed Atlas comet approached from this direction because that was its trajectory. If it had come from Ursa Major, we would have heard arguments about this region being strategically optimal for some other reason. The logic here is uncheckable. Any approach can be interpreted as intentional, and this is not science, but narrative. However, the most serious criticism comes from the absence of what should exist if the hypothesis were true. If the 3I Atlas is a technological artifact, it must emit heat. Any active system, any electronics, any propulsion generates heat. This heat must be emitted, not at wavelengths corresponding to several hundred Kelvin. Infrared telescopes must detect thermal radiation that does not correspond only to solar heating. Numerous infrared observations have been conducted. Specialized observations of Comet Tri-I Atlas have continued since its discovery. All available data, including images from the James Webb Space Telescope, ground-based infrared telescopes, and other sources, show thermal radiation characteristic of a cold, icy body being warmed by sunlight. No anomalies or unusual signals, just the comet behaving as it should. If the comet had any form of propulsion, we would have detected it through spectroscopy, chemical analysis, or changes in trajectory beyond normal evaporation. The 3I Atlas comet has been continuously observed since its discovery. Its orbit is known with high precision, and any deviation from a purely gravitational trajectory would be obvious. However, nothing of the sort has been observed. The comet strictly follows Newton's laws. There are no maneuvers, course adjustments, or evidence of active control. If there were communication, we should have detected it, but no laser pulses, modulated light, or other artificial signals were recorded. The CD community was observing. Several radio telescopes, including the Green Bank Telescope and the Allen Array, directed their antennas at the 3I Atlas during its approach, searching for any hints of artificial signals across broad frequency ranges. The result is complete silence, no hint of noise that could be interpreted as a signal. The background noise of the universe contains no artificial components. Tests conducted to distinguish technological signals from natural ones confirmed their absence. At some point, the burden of proof shifts to the supporters of the technology hypothesis. References to unlikely coincidences are no longer sufficient. Positive proof is necessary, something that cannot be explained by a comet and requires technological explanations. But such evidence does not exist. Statler emphasized this thought. We have outstanding tools. We observed the three-eyed Atlas intensely for several months. If there were something truly anomalous that disrupted the comet model and required new physical theories or classifications, we would have found it. The fact that it did not happen is, in itself, evidence, albeit not conclusive, but a significant argument in favor of natural origin. The scientific community's response was measured but firm. Articles are published, data is shared, observations continue. However, There is an unspoken agreement that the technological hypothesis no longer requires serious discussion. It has been tested and failed. Continuing debates on this topic distract from the real scientific opportunities offered by the Tri-Eye Atlas. The possibilities are truly immense. This is the first comet with a dense disk ever studied. This is the first object with a carbon dioxide to water ratio of 8:2. This is the first interstellar guest observed simultaneously by the James Webb telescopes, SphereX, and orbital devices on Mars. Data on composition can significantly refine models of planet formation in ancient stellar systems. Data on trajectory enhances our understanding of galactic dynamics and ejection mechanisms. The behavior of the comet during evaporation calls into question our assumptions about cometary activity and the distribution of volatile substances. But all this is lost when the conversation returns to the topic of alien probes. The scientists are tired of it. Tired of wasting time refuting statements that should never have gained popularity. Tired of seeing their work ignored because it isn't sensational. Tired of hints that they are closed to new ideas, insisting that evidence is needed before accepting unusual assumptions. Lind's comment that this is offensive speaks for itself. The team working on the Project Three-Eyed Atlas consists of some of the best observational astronomers in the world. They use advanced equipment, publish in leading scientific journals, and do exactly what science should do: observe, analyze, and draw conclusions based on data. And then they are told that they are missing the obvious, that they are so attached to traditional thinking that they cannot see what is right in front of them. This causes discontent. There is a deeper problem as well. The public perceives the situation as if scientists rejected the alien hypothesis without proper investigation. This is incorrect. The research was thorough. Multiple teams worked, different tools were used, and months of effort were spent. The hypothesis was taken seriously, thoroughly tested, and deemed unconvincing. However, since the tests were technical and negative results did not make headlines, public perception is that scientists appear unserious rather than meticulous. This perception harms science. It reinforces the opinion that traditional astronomy is too conservative, afraid of paradigm shifts, too invested in protecting existing theories. This is not the case. Astronomers would be eager to find evidence of extraterrestrial technology. This would be the discovery of the millennium, Nobel Prizes, rewriting textbooks, a complete change in understanding our place in the universe. There is motivation. There is will. But evidence is lacking. He correctly summarized in his blog, "The burden of unusual evidence lies on unusual claims, not the other way around. Science does not require absolute certainty in natural explanations before considering alternatives. It works by gathering evidence and following it wherever it leads. And now all evidence points to the comet. Unusual, interesting, scientifically valuable, but still a comet." The Three Eyes Atlas project will be observed in November and December. The JWST satellite will arrive in February. If something truly anomalous appears, if observations after perihelion show behavior that cannot be explained naturally, the conversation will change. Scientists will adapt. New hypotheses will be proposed. Testable predictions will be made. Thus, science progresses through evidence, not speculation. Until then, the technological hypothesis remains what it has always been: a possibility with extremely low probability, unconfirmed by data, supported by motivated reasoning rather than empirical foundation. Scientists studying the Atlas Triple-I continue their work, documenting this amazing visitor from the thick disk, extracting all possible information before it disappears back into interstellar space. With or without an alien narrative, with headlines or without, this is the work of scientists. Chapter 9. Social networks explode. Panic started on TikTok. A video published on September 29th was accompanied by dramatic music against stock footage of comets and spaceships. On the screen, text claims that Atlas's Triple-I is moving towards a collision with Earth. NASA is hiding the truth. The impact is expected on October 22nd. This video gathered 2 million views in 48 hours, thousands of comments. People are making emergency plans, asking whether to evacuate, checking distances to nuclear bunkers, all based on complete fiction. The claim of a collision was easy to refute. The closest approach of Atlas's Triple-I to Earth is 1.8 astronomical units, or 270 million kilometers, which is more than 1.5 times the calm distance to Earth. He never approaches us. Orbital mechanics are publicly accessible. NASA publishes ephemerides. Anyone with basic software can check the trajectory, but facts do not spread as quickly as fear. A video debunking the claims gathered hundreds of thousands of views, while a panic-inducing video continues to circulate to this day, generating comments from people who consider October 20th Second Judgment Day. Then statements about remote sensing emerged. An account named NY Crypto King posted on X that they conducted remote sensing of Atlas's triple eye. The post claimed they saw structures inside, microbial life trapped in ice pockets, and signals transmitted at frequencies we have yet to discover. The post contained a detailed description of the internal composition, the placement of technological components disguised as natural materials, and a warning that probes were launched on October the 29th, releasing microorganisms into Earth's atmosphere as part of a terraforming operation. Remote sensing as pseudoscience. Controlled experiments have repeatedly shown that it doesn't work. No one can see distant objects using psychic methods, yet the post still gained popularity. 30,000 likes, 15,000 retweets. People perceive this as credible information, building theories around it and comparing it to other theoretical constructs. The claim about the signal became particularly viral. Many radio enthusiasts began to track frequencies that they believed could be transmitting this signal. They found nothing but convinced themselves that the signal was encrypted or used modulation schemes beyond human capabilities. The discussion was joined by 4chan with a post claiming insider information. An anonymous user, identifying as a European astronomer, stated that the triple eye of Atlas is neither a comet nor a spaceship. This is a bubble of dark matter or dark energy, left over from the Big Bang. The object does not reflect sunlight. It absorbs energy from the quantum vacuum. It is heading towards Earth to merge with its core and cause a shift in dimension. The post was clearly fabricated. Its physical aspects made no sense. Dark matter does not form bubbles and does not absorb vacuum energy, but the post was screenshot and spread across various platforms as if it were a leak of classified information. The connection to Jeffrey Epstein emerged in early October. Someone on Reddit noted that Loeb's first significant work on the three-eyed atlas was published 72 years after Epstein's birth. They calculated that the date of the comet's discovery, July 1st, holds significance in numerology. They added some selective correlations between orbital parameters and dates related to Epstein's life. Ultimately, they concluded that the whole event with the three-eyed atlas was fabricated to distract from the renewed interest in Epstein's affairs. The conspiracy theory seemed absurd. Comets do not appear on predetermined dates for political purposes, yet it has spread, mingled with QAnon ideas, and is cited as evidence of government manipulation. Other versions of the theory directly targeted Loeb, claiming that his analysis of the three-eyed atlas was discredited due to his Jewish heritage. Due to Israeli connections, as Harvard receives funding from sources linked to the geopolitical opponents the author wanted to mention. These were not good faith critics, but anti-Semitic attacks disguised as skepticism. Loeb responded in his blog, stating that the three-eyed atlas exists independently of his identity and that the object can be observed by anyone with a telescope. His ethnicity and nationality have no bearing on physics, but fighting bias is exhausting. Posts continued to emerge. Threats from NASA became an important topic of discussion. In early October, a government shutdown began in the USA. NASA's Public Relations Office stopped updating its websites and social media. Press releases slowed down. The temporary information lull coincided with the three-eyed atlas approaching Mars and hiding behind the sun. Conspiracy theorists saw a causal connection. The pause was intentional. It was time for NASA to avoid questions about what the Martian orbiters had seen during their flybys. The agency concealed data, hiding images that showed fragmentation or the deployment of the probe, or anything else they did not want to disclose. In reality, government shutdowns are political failures, not well-thought-out cover-ups. They occur when budget negotiations fail. The timing was random. NASA was hiding nothing. Data from the Martian orbiter is processed under normal conditions for several weeks. The suspension delayed the process, not due to censorship, but because employees were temporarily suspended, halting work. When the government reopened, the images were published. They showed the comet, as expected, but by then, the narrative was already set. The delay became proof of a conspiracy, regardless of what the data ultimately showed. The fact-checking group Al Jazeera Sanad examined the claims circulating in Arabic language social media. The post claimed that the comet Three-Eyed Atlas would strike Earth on October 22nd, saying its tail would poison the atmosphere and electromagnetic pulses would disable all electronics on the planet, referencing religious prophecies that the signs had already begun to come true. Sena traced the source of these claims to incorrect translations and deliberate falsifications. He published a detailed rebuttal, citing sources and expert opinions. But his fact-checking reached only 10% of the audience that saw the original false statements. A viral Facebook post reported that the Three-Eyed Atlas prompted an emergency military meeting. World leaders gathered in secrecy, activating defense systems. Quotes from anonymous Pentagon officials hinted at a national security threat. The post refers to a YouTube video with 3 million views, lasting 40 minutes, where the narrator explains how the Three-Eyed Atlas was discovered by secret military satellites before it was noticed by civilian astronomers. It was said that the trajectory was initially hidden, and how information leaked through unofficial channels. None of this had any basis. All of it was presented with dark music and an authoritative tone, adding to its plausibility. The religious aspect became particularly noticeable. Christian fasts interpreted the Three-Eyed Atlas as a sign of the last days, referencing revelation and connections with the worm. The comet was seen as a harbinger of judgment. Islamic fasts discussed similar themes through the lens of various sacred texts. Hindu interpretations concerned cosmic cycles and avatars. People from different faiths projected apocalyptic narratives onto an object that was simply ice and stone. The need to find meaning in celestial events has existed since ancient times. Comets have always been harbingers. The Three-Eyed Atlas was no exception. Now omens spread across the world in just a few hours, rather than taking years to reach people's consciousness. Meme culture also played its role. The images of the Three-Eyed Atlas were captioned in various ways. The homework I forgot to submit has finally appeared. My problems arrived on time. The aliens Taurus came to check if Earth is worth visiting and decided to leave. Memes were harmless and often funny, but they reinforced the idea of the Three-Eyed Atlas as a character in a story rather than a scientific object, giving it traits of personality and intention. Anthropomorphism complicated the interaction with real data. People reacted to the comet emotionally rather than analytically. The polarization was evident. On one side, astronomers and scientific observers tried to convey accurate information, spectra, orbital calculations, composition analysis. On the other side, a tsunami of speculation, conspiracy theories, fear, and dreams. Two groups barely intersected. They inhabited different informational ecosystems, on different platforms, with various standards of knowledge. A person could spend hours consuming content about the Three-Eyed Atlas and never encounter a single accurate fact. The Twitter community of notes tried to keep up by adding context to viral posts and referencing NASA pages, providing orbital data to debunk collision rumors. However, the community notes appear only after the post has already gone viral. Correction reaches only a small part of the audience. Cognitive bias proves strong. People who want to believe in the hypothesis of an alien mothership find ways to ignore refutations. NASA lies. Scientists are closed to new ideas. The official version doesn't add up. Everything that contradicts the preferred narrative is discarded. YouTube has turned into a battlefield. Scientific channels struggle to explain what the three eyes of Atlas are, what observations show, and what the chemical composition means. These videos hardly gather more than 100,000 views. Meanwhile, conspiracy channels with bright thumbnails and sensational headlines attracted millions. The algorithm favors engagement over accuracy. Fear drives engagement more effectively than education. Thus, misinformation is promoted, amplified, and monetized. Communities on Reddit split along predictable lines. Astronomical and space subreddits maintain reason. Moderators delete conspiracy posts. Users debunk claims with references, engaging in civilized discussions about trajectory uncertainties and spectroscopic methods. But other subreddits focused on UFOs, conspiracies, and irregular topics turned into echo chambers. Any skepticism was met with negativity. Any reference to mainstream science was seen as propaganda. A self-radicalized community convinced each other that they understood the truth, while everyone else was blind or complicit. Influencers on Instagram, lacking scientific education, posted confident explanations about Atlas's three eyes. Many made gross mistakes, confusing astronomical units with light years, claiming that a comet could be seen with the naked eye, although it was impossible, confusing Atlas's three eyes with other objects, but they had audiences. Hundreds of thousands of subscribers trusted them, sharing their posts, perceiving their influence as equivalent to peer-reviewed research. Disinformation had real consequences. Astronomers received panic letters, teachers tried to calm students who thought the world was ending, and psychologists faced anxiety caused by apocalyptic narratives. The damage was not hypothetical, but measurable, quantitatively assessed in the lost time spent correcting false claims and the psychological stress inflicted on vulnerable people. Part of the conspiracy beliefs was a peculiar representation, a trolling of those who understood more but took pleasure in creating chaos. But part of it was sincere. True believers were convinced that Atlas's three eyes represented first contact, an existential threat, or divine intervention. These people stubbornly insisted on their views when confronted with counterarguments, sought information that confirmed their beliefs, and constructed complex schemes linking Atlas's three eyes to other conspiracy theories. The object became a symbol, a white canvas onto which people projected their fears, hopes, and fantasies. By mid-October, the three eyes of Atlas had ceased to be just a comet. It became a cultural phenomenon, reflecting how society perceives information in the age of social media, how truth and fiction blend, how expert opinions are devalued, and how fear spreads faster than understanding. The object, a 5-kilometer sphere of ancient ice and stone hidden behind the sun, became almost insignificant to the narrative surrounding it. The scientist studying the three AIs could only observe. He could publish articles, give interviews, make amendments, but he could not control the story. This story broke free, mutated, and became something inaccessible to him. All he could do was continue his work, document observations, analyze data, and hope that eventually, long after social media faded, scientific records would maintain their accuracy and serve as a foundation in the chaos. Chapter 10. The Moment of Truth in November. JWST was 428,000 kilometers away from the 3I Atlas on November 4th. This is closer than any spacecraft has come during observations after perihelion. The researcher of Jupiter's icy moons was not intended to observe comets. He was created to study Europa, Ganymede, and Callisto, the icy crusts above subsurface oceans, the radiation conditions around Jupiter, and the interactions of magnetic fields. However, spacecraft are adaptable. Mission planners can change the course, and from November 2nd to 25th, JWST will allocate time to observe an interstellar guest, collecting data while ground telescopes still face difficulties due to proximity to the Sun. The toolkit is impressive. JWST, an optical camera, will take pictures of the nucleus and coma with a resolution that no other spacecraft can surpass during this period. MAGES, a spectrometer, will map the composition in the infrared range, tracking the distribution of various volatile substances in the coma. The UVS, ultraviolet spectrograph, will detect emissions from excited atoms and molecules based on rapid observations from August, but with higher spectral resolution. PEP, a particle package of the environment, will measure the plasma and neutral gas around the Tri-I Atlas, documenting the interaction of solar wind with cometary outgassing. This is a critical moment. The Tri-I Atlas emerged from perihelion on October 29th. Whatever happens at the moment of closest approach to the Sun, maximum heating, peak emissions, potential fragmentation, or deployment of probes, all evidence will be visible in November. The comet should be bright, active, and possibly changed. JWST will document these changes from a perspective that ground instruments cannot reproduce. However, there is a limitation: communication bandwidth. JWST uses a medium-gain antenna, as the high-gain antenna is currently serving as a thermal shield. Data transmission speeds are reduced. Images and spectra are stored on board. The uploaded November observations will not reach Earth until February 2026, meaning 3 months of waiting. 3 months during which we will not know what JWST saw, whether the comet survived intact, if it broke apart, or if unexpected moments appeared in the data. Ground observatories will begin tracking 3I Atlas at the end of November, when the angle of solar scattering increases and twilight observation becomes possible. When the comet emerges from the bright light and becomes accessible to large aperture telescopes, forecasts vary. Some models predict brightness at a level of 10 or 11, which will be sufficient for 8-inch amateur telescopes in a dark sky. Other models are more restrained, expecting brightness from 12 to 13, which will require professional tools or special amateur setups. The brightness will immediately indicate whether something significant has occurred. If the 3-eye atlas sharply increases its brightness, if passing perihelion causes a powerful outburst or opens new volatile substances, then the brightness will be higher than expected. If the comet breaks apart, the overall brightness may initially increase due to the greater exposed surface and then decrease as the fragments disperse. If it falls into hibernation, if the volatile substances run out, or activity suddenly ceases, then the brightness will be below the expected level. All this will become apparent in the first few nights of ground observations. The observatories of the Galileo project are operational. 3 sites constantly watch the sky, in Massachusetts, Pennsylvania, and Nevada. In November and December, the detection thresholds will be lowered. Any temporary object, any unidentified moving object will be marked. The forehead does not hide its expectations. If the probes were deployed at perihelion, using retrograde maneuvers to enter Earth's orbit, they could arrive between November 21st and December 5th. Observatories are tracking exactly this: small objects in unusual orbits, trajectories that do not match satellite catalogs or space debris, anything that might hint at artificial origins. The probability is low. Everyone acknowledges this, but the cost of observations is minimal compared to the potential return. If something appears, if an object that cannot be explained by natural causes is on the horizon, the game will change instantly and radically. Every telescope in the world will focus on studying it. Space agencies will rush to plan intercepts or close observations. The scientific community is mobilizing like we haven't seen since the first detection of gravitational waves or the confirmation of the existence of exoplanets. And if nothing appears, if November and December pass without any probes, then the technological hypothesis will lose its last support. The Loeb scale rating will decrease. 3-eye atlas will definitely be classified as a natural comet, unusually large and chemically anomalous, but still natural. Speculation will cease, science will continue, and history will become one of discovery and characterization rather than contact with aliens. The Europa Clipper spacecraft, recently launched as part of NASA's mission to Jupiter, is on its way, but has not yet reached the planet. Discussions are underway for coordination between Clipper and JWST. Both spacecraft are equipped with ultraviolet spectrographs that can observe the 3-eyed Atlas comet from 2 different points simultaneously, allowing for parallax, stereoscopic observations, and 3-dimensional information about the comet's structure, inaccessible to a single spacecraft. However, the geometry of observation is not ideal. The Clipper is not in the optimal position, but if the opportunity arises, mission planners will take advantage of it. Real scientific data will be obtained by comparing the states of the comet before and after perihelion. We have data from August from the James Webb Telescope and September data from Martian orbiters. These observations recorded the approach of the Tri-Eye Atlas comet to perihelion while it was still relatively cold and emitting gases in moderate amounts. November. Data from JWST and ground-based telescopes will reveal the consequences. The comet has heated up, experienced stress, and possibly undergone changes due to its closest solar approach in its 10 billion-year history. The comparison of these datasets will show how interstellar comets react to perihelion, how their chemistry changes, and how their structure withstands or fails under thermal shock. The ratio of carbon dioxide to water is particularly interesting, being 8:1 in August. Will it remain the same in November? Or will the warmth from perihelion preferentially drive out carbon dioxide, exposing icy water and changing the ratio to a more typical one? If the ratio changes, it will indicate a layered structure of the comet: carbon dioxide-rich outer layers and water-rich inner layers. If the ratio remains constant, it will indicate a homogeneous composition. Both options have scientific value, but tell completely different stories about how this object formed and evolved. The development of the comet's tail is also an important indicator. Pre-perihelion images showed a faint tail or its absence depending on exposure time and instrument sensitivity. After perihelion, the tail should become visible, stretching millions of kilometers, curved under the influence of solar pressure and orbital speed. Spectroscopy of the tail will reveal what particles are ejected, whether silicate, organic, or icy. The distribution of particle sizes will provide us with information about erosion processes. Small particles indicate active sublimation, while larger ones may signify mechanical destruction or explosive events. If the three-eyed atlas has cracked, the tail will show complexity, multiple streams, and overlapping structures. Each fragment will contribute to the tail, all mixing in terrestrial images, but can be resolved with careful photometry and positional measurements. Theoretically, the Hubble telescope could capture the structure of the tail if observation time could be obtained. It would be possible to allow individual contributions of fragments to create a map of debris distribution, but time on Hubble is very precious. The number of observation requests exceeds available resources by 5 or 10 times, and obtaining permission for additional observations is not guaranteed. The Vera Rubin Observatory is not yet operational. Its first launch is still months away, but when it begins to work, it will be a true revolution in the detection and characterization of interstellar objects. The Large Synoptic Survey Telescope, as it was originally named, will scan the entire visible sky every few nights, conducting deep exposures and automatically identifying moving objects. Rubin will be able to detect interstellar visitors while they are still far from the Sun and weak. He will track them through perihelion and beyond, constructing curves with thousands of data points, while spectroscopic observation using other tools will rely on detailed photometric monitoring conducted by continuous observation from Rubin. The object 3 Eyes of the Atlas is a prototype that teaches us what to expect from future interstellar comets, how their brightness curves look, how their activity develops, what spectral features appear, and when. Each observation of the 3 Eyes of the Atlas helped in the design of research for Rubin, refined detection algorithms, and calibrated models. The next 3 Eyes of the Atlas, the fourth interstellar object, will be discovered faster and characterized better thanks to the lessons learned from this. Observations in November are also important for refining trajectories. Each measurement of position improves the orbital solution, reduces uncertainties, and allows for better predictions of where the 3 Eyes of the Atlas will be in December, January, and beyond. When the comet passes by Venus, near Earth's orbit, heading back to the asteroid belt, tracking becomes more difficult. It dims, moving among increasingly cluttered fields of stars, so it's important to have precise coordinates to avoid losing it. Ground-based telescopes must be precisely aimed so that observation time is not wasted searching for an object that should be in view, but is not visible due to slight coordinate inaccuracies. JWST's measurements of the plasma environment are unique. No other spacecraft will be close enough to explore the interaction area where the solar wind meets the gases emitted by the comet. This boundary, the comet pause, is dynamic, constantly changing depending on variations in ejection speed and solar wind pressure. PIP will measure ion density, electron temperatures, magnetic field fluctuations. All of this will be used in models of cometary magnetospheres, how charged particles accelerate, how energy enters the comet. For 3 Eyes of the Atlas, plasma data may reveal something subtle about the composition. Different volatile substances ionize at different rates and form various types of ions. The mass spectrometer component Pu can distinguish between water group ions, carbon dioxide ions, and others. If unexpected views appear, if the plasma composition shows molecules that have not been spectroscopically detected, this will be new information. Additional constraints on which icy substances are truly present and which we have assumed based on remote observations. February 26, 2026 seems distant. 3 months is a long wait for data about the comet, but it is necessary. The spacecraft has limited bandwidth. Scientific research takes precedence over public interests. This data is worth the wait. They will be processed, calibrated, and analyzed by specialists who understand the tools and can extract signal from noise. When the results are published, they will be final. This will be the best characterization of the comet after its perihelion that we can achieve, given current technologies and mission constraints. Until then, we rely on ground observations, amateur astronomers with telescopes in their yards, professional observatories trying to fit the study of the comet into their busy schedules, spectroscopic campaigns organized in international cooperation. Every clear night is important. Each observation adds data, and slowly, frame by frame, spectrum by spectrum, the story of what happened at perihelion begins to clarify. The comet does not care about our curiosity. It does not know that we are watching it. She simply continues her path, emitting gases or remaining inactive, whole or fragmented, natural or against all odds, something else. The comet moves through November, ignoring the telescopes tracking it, the instruments analyzing its light, and the heated debates about its nature. It simply exists. From our tiny observation post 93 million miles from the Sun, we desperately try to understand what it means before the comet disappears into the darkness, taking its answers with it.